Okay, so without further ado, I'll introduce David. He's going to tell us about his work. As I mentioned, it won the Best Paper Award at NeurIPS, Neural Ordinary Differential Equation. Work with Ricky Chen, Yulia Rubanova, how would I say it? Rubanova, much better. Jesse Betancourt, and David. Go for it.
Do you guys have the feed from here? All right. Can everyone hear me? Wonderful. OK. It's great to be up here. So today I'm going to be telling you about a new class of neural network architectures based on ODE solvers. So for those of you who haven't thought about ODEs in a while, here's a quick review. The setting is that there's a vector-valued state, Z, such as the position and velocity of a system of particles, or maybe the concentration of chemicals in a chemical reaction. And this state can change continuously with time. We're given some function f that defines the derivative of the state with respect to time. And this defines a gradient field that is a function of both the state and the time. So what we usually do with ODEs is we solve initial value problems. The idea is that we're given the state at some time t0, and we need to compute the state at some future time t1. So this requires integrating the derivative of the state through time, and usually has to be done approximately with a numerical solver. The oldest and simplest numerical method for solving ODEs is Euler's method. So Euler's method is usually considered a poor ODE solver because it doesn't control its error in any meaningful way. So the way Euler's method works is that we start at some initial state, and we move in the direction of the gradient field at that point for some finite step size. And then we start there and move another step in the gradient field starting at that point. And the problem here is that the error grows as we follow this approximate ODE path. However, there has been hundreds of years of work on adaptive ODE solvers. And these have sophisticated evaluation and extrapolation strategies that let us solve ODEs to, well, pretty much any desired tolerance in many fewer evaluations. OK, the other bit of background I have to give, for those of you who haven't been following deep learning in the last few years, is that there's been an embarrassingly simple change to network architectures that's made a huge difference in how easy they are to train. So the standard deep architecture just says that we start with our input x, we put it through one, let's say, a layer of a neural network or something like that, so some basic building block. And then we feed the output of that to some other building block. And we keep feeding these into each other until we have some deep architecture. So now what everyone uses to train is residual networks. And the only difference here is that we say, OK, take the input x and add the identity function. Right? Don't just put x through some function, also add x back to the end. So at every layer, we add on the result from the previous layer as well as feeding it through our function. So the intuition here is that it's easier to learn the change needed to improve an almost correct answer than it is to completely transform an answer at every level. So the idea is that the f's on the right-hand side have an easier job to do. There's also some intuitions about how gradients are easier to flow through this model. OK. So many people have noticed that there's a close connection between residual networks and Euler integrators. And let's look at the code for a Resnet. So first, we have to define our little block of computation. We'll just, in this little f, it takes this data time, the state, the time, and some parameters, and it just calls, let's think of like a one hidden layer neural network here. OK, and then the code for the residual network says, for every layer, we'll just update the state according to f. So this looks just like Euler integration with a step size of 1. On the right, we can see now what this looks like when we execute a residual network one layer at a time. So we start at layer 0. The input is x, and we just keep adding some change that depends on the current state. OK, so how far can we take the connection between ODEs and neural networks? Well, if we look at this Resnet, we can make one simple change to make its dynamics defined continuously as a function of depth at any sort of layer, even in between the integers. So looking at this, the definition of f up here, I can say, well, what if the network got to see depth as an input, right? So we can just pretend that that's a real valued number and feed it in as another input to our neural network. We just have to make it a little bit larger. And then we can have one set of parameters used for the entire depth instead of going back. We used to have a different set of parameters for every layer, and now we have one set of parameters, but the layer gets to know which depth it's at. So all we're doing is reparameterizing a Resnet so far. But now this means that the dynamics are defined even between layers. So this is like our new gradient field. So the model actually does define an ordinary differential equation, and evaluating it can be viewed as solving an initial value problem. But we're still using this primitive Euler's method to solve this ODE. So one thing we can do, we're totally free to replace Euler's method with any more sophisticated adaptive ODE solver. So we call this model an ODE net. And so the entire recipe for defining the architecture is take the old blocks, the old neural network architecture that you use to define the layers of your Resnet, and instead of calling this sort of iterative Euler's method, just send the whole thing to some black box ODE solver. And so in the first iteration of this work, we actually were calling the Fortran solvers like in LSODA that were written, over the last 40 years in Fortran. Okay, so we can see this. So we can watch this network evaluating the dynamics wherever it needs to get the answer with any desired tolerance dynamically. Okay, so I want to say that it's not like we came up with the idea that you can view ODEs as, or neural networks as ODEs. So there's been actually a lot of work on this. So first of all, in the early days of neural networks, the reason they're called neural networks is because people were inspired by the human brain, which is a continuous time system. So the early papers that looked at these models said, let's look at a continuous time model and then approximate it with these discrete layered neural networks. There's been a lot of work in just the last couple of years making this connection more explicit. So there's been a few papers from UBC talking about how to build better architectures that are inspired by good ODE solvers. Or to say, can we make our training methods look like, use these connections to have better training methods. Okay, but the reason that people didn't actually train these methods before is that it's really awkward to compute gradients with respect to the parameters of this ODE network. Or at least it wasn't a well-known trick in the deep learning community. It is known how to do this in the numerics community. So what we have to do is somehow get the gradient of some scalar objective, this is like our training loss or something like that, through the ODE solution. So you might think that we can just simply backpropagate through the operations of this ODE solver, and you would be right. I mean, it's just a bunch of linear algebra that's running on our computer. So automatic differentiation can tell us how to backprop through all those steps. But there's two reasons why you wouldn't want to do this. So one is that this has high memory cost. So if you want to do efficient differentiation, then you need to do reverse mode, which requires storing all the intermediate quantities that the solver evaluates along its entire path. So in practice, this is, I know this doesn't work. Secondly, we introduce extra numerical error. Like the ODE solver is trying to control the error of the output of this function, but it takes as sort of long steps as it can to get there on the way. So the gradient with respect to the parameters might have extra error. So there's a general sort of rule that I like to follow, which is you should approximate the exact derivative and don't differentiate through your approximation. Okay, so to be more concrete about how this works, so here are the equations for the standard backpropagation rules. So we just start from the scalar loss at the end and chain the gradients back through every layer. And then the second equation says, how does every layer's hidden state depend on the parameters at that layer? So it turns out that in the 60s, the continuous time version of these equations was worked out actually by this blind Russian mathematician, Pontryagin. So if we take the infinitesimal limit of sort of having more and more layers in our neural network, and each of them does less and less work, we end up approaching this system of equations, which is called the adjoint sensitivities method. And we have to define this A here, which has an analogous quantity in the original backprop. It has dynamics that are defined by this vector Jacobian product. So A is a vector. This df dz is a Jacobian. we can write down these dynamics and have them be automatically computed for us by automatic differentiation. And then the total derivative with respect to theta is just another ODE. And that's OK, because we can just send that to an ODE solver, too. So to make this even more concrete, we write a little bit of code. So when we want to compute the gradient, we have to define these augmented dynamics, the dynamics of this system, that requires knowing the original system state, this adjoint, and then keeping track of the sum of these partial derivatives. So we know f. F was given to us here. And then these vector Jacobian products are things that automatic differentiation can give us efficiently and automatically. So these will cost, evaluating those two quantities there will cost about the same as evaluating f. These are the same calls to autodiff are made in the standard backpropagation. We just don't sort of break them out. So then, so if we want to now get the total derivatives, we just send this new augmented larger system to another ODE solver. So the way this works is that on the forward pass, we call our ODE solver to get the output of our neural network. And then on the reverse pass, we call another ODE solver going backwards in time to get the gradients. OK. And so the nice thing about this, well, we can kind of show this graphically. The nice thing about this is now we have constant time gradients, or sorry, constant memory cost for our gradient evaluations. So there's no need to store. So the cool thing about ODEs is that you can run them forwards or backwards in time. Obviously, you can introduce a little bit of extra numerical error here, but that's not a serious problem, and that's controlled by the ODE solver. So in standard backprop, as I said, we have to store all the intermediate quantities that are being computed by the neural network as we go. In a ODE net, we can actually just run the system backwards from the final state to reconstruct all the hidden activations as we go. So we just run this combined system backwards in time together. And actually, another bit of work done by researchers at Vector, including Roger Gross, designed a deep Resnet architecture that did have reversible dynamics in order to get to this constant memory training cost. And then the drawback there is that you have to restrict the layer architectures to look kind of like some sort of leapfrog, update one half at a time system. Here, this will work for any dynamics that we want. OK, so now we have this new differentiable model component, just an ODE solver, that we can stick anywhere we want in our models. So in particular, anywhere where we have a set of Resnet layers that transform something in like R to the D to R to the D, we can replace them all with a single ODE net. So besides, well, right. And so we can train this new sort of composite model with the same method that we used before, which is just stochastic gradient descent. And the first thing we did with this model is train it on MNIST, and we got the same test performance. So the funny thing about these ODE nets is that they don't really have a notion of depth. The thing that's closest to depth that we can talk about is the number of evaluations of the dynamics that the ODE solver makes. Let's see. So here the black dots show where the ODE solver evaluated the dynamics in order to compute these trajectories for different inputs. So to be clear, this is just a toy system, a one-dimensional hidden state, mapping from inputs to outputs. Each of these black lines is the trajectory saying, if I have this input at the bottom, where will it end up at the top? OK. So one interesting thing is that the dynamics become more demanding during training. So when we started with just random weights, it didn't take that many evaluations to solve the system to a desired tolerance. And then as we fit the function better, the dynamics become more demanding to compute. So the cool thing here is that depth is just a detail that we delegate to the ODE solver. And we say, just give me whatever depth you need in order to compute the answer. OK. So the downside of doing this is that we can't directly control the time cost of our models during training. Right? With a standard neural network, you can just say, I have 10 layers. I know it's going to take this much time to compute. Here, we don't know how much time it's going to take to compute until we actually run the network. So in practice, this was about like 2 or 4 times as expensive as a standard architecture. Interestingly, there was a paper from last year that built a schedule for gradually increasing the depth of a ResNet during training, sort of by hand, because they thought this would make sense, that at the beginning of training, your dynamics are simpler, so they should need fewer layers. And here we get this happening just sort of emergently, automatically. Okay, so although we can't control the time cost of the model during training, we can control the time cost at test time. So a really nice feature of modern ODE solvers is that they can explicitly trade off between the speed of evaluation and the precision of the answer. So here, the blue line shows the error ceiling that we've given the solver. We say, give me the answer to within 10 to the minus 4. And when we plot the actual errors that were attained in a real ODE net, they're all within the error tolerance that we asked for. And the x-axis here says, how many evaluations did it take to get that error. So we can loosen the tolerance further at test time, and now the number of dynamics evaluations that it takes to get that tolerance decreases. As the time cost of the network, so the time cost of the network decreases while the solver still meets its tolerance, and compared to using something like low precision floats or binarizing your weights or something like that, this is a much more fine-grained and continuous way to control this trade-off. One nice thing that happens by using adaptive ODE solvers is that we can find efficiencies wherever they lie. So you might ask, well, solving the forward system is one thing, but solving this reverse system is actually a much larger system. It has twice as, has the original state plus the adjoint plus keeping track of this integral over all parameters. It might be much more expensive to compute. And I think that there are probably cases where that happens. But in the network, the first network that we trained for this paper, when we compare the number of forward evaluations that it took to reach the desired tolerance versus the number of backwards, it actually took half as many evaluations on the reverse pass. So if we had just been doing naive backprop through the layers, we wouldn't have been able to pick up this extra efficiency. Okay, so now that we can fit ODEs with gradient descent, we can put them anywhere in our models. And one exciting use case in my mind is using them to build better time series models. And in fact, that was the original motivation for this whole project, was trying to model hospital time series data with Euler. And we decided, well, why don't we just use an ODE? And then it turned out people didn't know how to train them, and then that led us to this. So specifically, we can now train sort of physics-style models in which a latent system has continuous time dynamics. And we can add any sort of complicated noise model we want to the observations. So these observations could just be, add Gaussian noise, like in a Kalman filter, or they could be something as complicated as, the X's are medical records, and there's a whole language model going from the latent state to our observations. So unlike recurrent neural networks, these models have a well-defined state at all times, even in between observations. And they decouple the system dynamics from the task of doing inference about the data that we've seen. Whereas in an RNN, they're kind of all jumbled up into one giant neural network. So this lets us handle data that arrives at irregular intervals in a principled way. So I won't go into the details too much for time, but the way we train this model is as a variational autoencoder. So we, in this paper, use the recurrent neural network to encode the entire sequence, and then we use the ODE to define the sort of decoder that says how does the data actually depend on this hidden state. But in follow-up work, we've designed an encoder that reuses the dynamics of the decoder in the encoder and just runs things backwards in time. Okay, so how well does this work? Well, here we show results on a toy problem specifically chosen to make our model look good, where we have some 2D observations made at irregular times. So if I haven't made it clear, so standard RNN architectures need to have the data arrive at fixed intervals. There's sort of variations where you can tell the RNN what the sort of change or what the interval to the next data point is. But the problem is that this doesn't give you a well-defined state in between times. And it's not really clear how you should extrapolate either. So we sort of did the most sensible thing we could think of to get an RNN to handle irregularly timed data. But it still doesn't really extrapolate very well or fit the data, whereas our latent ODE does a nice job of this. Okay. So for any computational neuroscientists in the room, you can also add a Poisson process likelihood to this model that says, not only can this model handle the fact that the data came at irregular intervals, it can condition on the fact that you did see a particular observation at a particular time. So for instance, if someone comes into the hospital on a certain day, that already tells you a lot about their hidden state. And so the standard way to do this for continuous time models is like having a Poisson process likelihood. The reason people don't usually use them is because they have a time integral in them. But now time integrals are just something that we can add to our model wherever we want. So here's a toy experiment where we said, OK, there's some latent state, some rate of events that depends on the latent state. And if we see these events at these times, what do we infer about the latent state? And it's like high where there are rates. Right? OK, so the most exciting to me, though, application of this work turned out to be in density modeling. OK, so I'm sure anyone who's taken calculus has seen the change of variables formula that says if I have some original variable z and I put it through some function f, the change in density is given by the log of the determinant of f, or rather the determinant of the Jacobian of f with respect to z. So this is true for any invertible z, and it's a great formula, but it's too expensive to compute in practice. So it costs d cubed time to compute this determinant for like if you just don't have any other properties that are known about f. So it wasn't too hard for us to ask and find out, OK, what happens now if we have some sort of instantaneous change in the state of f, or in the state of z, given by some f? Then it turns out that the instantaneous change in density is given by the trace of the Jacobian. And this is really good news. So compared to det, trace is a linear operator. It has d squared cost in general. But there's actually a whole bunch of tricks we can use to approximate the trace really easily. And now we don't even need f to be invertible. We just need it to be continuously differentiable everywhere. OK. So what we use this for is to define a density model that would let us basically, a parametric, tractable, normalized density model, which is a hard thing to build, right? Like think mixture of Gaussians. So the idea is that it takes a Gaussian at time 0 and then continuously transforms it according to some f that we define using a neural network. And then by keeping track of this instantaneous change in density, using another call to an ODE solver, we get some normalized density at the top. So this is a really nice way to stick tons of parameters into a density model and still have a closed form density. So we call this continuous normalizing flows. And again, we can just train this by SGD. So compared to like GANs or VAEs, there's no need for a recognition network or a density network. It's just like fitting a mixture of Gaussians or something. It's really easy. And there's no need for us to restrict the architecture of F. It can just be any neural network you want, like, for instance, a convolutional layer. So here's a toy example of us learning a transformation from data on the up left. That's a data set we made that's shaped like a leaf. And now what I'm going to show you is after we've trained this model, it's going to know how to turn a Gaussian into a data density that matches that data set. And again, the way that it does this is by taking that Gaussian and then putting every point through this vector field. And the vector field itself actually depends on time. So here we go. OK. So great. So the important part is that we can evaluate the density of this model for pretty cheaply at every point, which is not something you can do with a VAE or a GAN. So just to show you again. OK. And just in case you want to see that it can work on any density, here's a few sort of toy problems that we played around with just to make sure that it could do things like handle sort of step functions in the density. OK, so we actually already wrote a follow-up paper with my student, Will Grathwall, that uses the Hutchinson's trace trick to scale up this model to high dimension. So for instance, now we can use it to model images. We just treat the image as a high-dimensional vector, and we learn what the model has to learn is how to turn a Gaussian, just a random Gaussian noise vector of the same size as the image into an image. So what I'm going to show you here is these are, in each corner is a different random Gaussian vector, and us interpolating between those random Gaussian vectors. Right? It doesn't look like anything. And now I'm going to show you, if we run these Gaussian vectors through the learned dynamics, then they get turned into things that actually look like images. And of course, just like any latent variable model, now I'm showing we can actually interpolate between images. So it goes from horse to cat to boat to car. Right. So it's still early days, and this model is slower than some bespoke image model like GLOW and real MVP. So the open problem here is how do we regularize the dynamics to be fast to evaluate? I'm going to come back to that. Okay, yeah, and so I want to say that we got this to work on image models just so we could show that it scales, but the real win comes from just unstructured tabular data. If you have some customer records or something like that, this will do a really good job of modeling that. The reason that it's hard to be, we match the state-of-the-art performance on images, but at the cost of this extra computational cost. The reason it's hard to compete in images is that there's this nice convolutional structure that we can sort of bake into the models. And so the competing models are already sort of specialized for images. Ours is much more general, but it's hard to show you that we do a good job of density estimation in some other domain other than images, except by a table of numbers. So, okay, so if anyone here has worked in ODEs, I'm sure you've been chafing this whole time and saying but how do you know that this is actually a normalized density? How do you know that you've actually achieved the errors that you say you achieve? Because ODE solvers have sort of asymptotic guarantees about whether they meet their error targets, but they don't guarantee that they'll meet their targets every time. And you can always come up with counterexamples for any ODE solver that it will think it solved accurately, but it actually didn't. So we did one more experiment where we actually asked, okay, for a one-dimensional density, we can actually just integrate it over its whole domain and check whether it sums to 1. And so here we did this. And of course, the accuracy of the normalization of our learned models depends on what the tolerance is we gave to the solver. So again, for all of these experiments, we had to choose a tolerance to say, okay, solve this gradient to within 1 part in a million or something like that. So reassuringly, the lower that we set the tolerance, the the better answer we ask for from the solver, the better an answer we get. And the data densities that we report actually do sum to 1, at least in this one-dimensional example. There's no way for us to do this exhaustive integral in more than a few dimensions. Okay, so one nice thing about this project is that PyTorch code is available. So we've implemented a suite of adaptive step solvers, including Ring-Okuda and adaptive order atoms. These are sort of the standard workhorses of solving numerical ODEs. So these are implemented in PyTorch along with the adjoint sensitivities method that lets us not differentiate through their operations naively. And then also the code for this follow-up fjord model. So yeah, if you train ODEs for other reasons, you're a biologist, now you can stick a neural network in your biology model if you want, or you can just stick an ODE in your deep net anywhere you want as well. Okay, so to recap, we have presented a new family of continuous depth architectures, and they adaptively compute their answer instead of following a fixed recipe. They have constant memory cost for training. They can automatically trade off speed for precision in this fine-grained way. And you can use them also to build time series models that let you handle irregular observation times, although it's still early days. And also, we can use this to define a new class of generative density models that don't have a recognition network or anything like that. Okay, so what are the next steps? So the things that we've been working on since then is to say, well, this latent ODE time series model is pretty nice, but the problem is that it has deterministic dynamics, which means that if there's something that happens to the person we're observing that we don't directly observe, it's kind of hard to incorporate that into the model. So we are trying to generalize this model to latent stochastic differential equations that says there are unseen perturbations all the time that are happening to your patient that you have to model somehow, but you don't get to directly observe when they happen. And the sort of technical obstacle here is to make sure that we have a stationary distribution. But when we do have that, it's really nice because then that lets us skip doing inference over the regions where we don't have any data. So, okay, so the other major direction that we're working on is regularizing the dynamics of this neural network to require a few evaluations. So I showed you that plot where the number of evaluations required increased as we trained. And that makes sense because nothing in our training procedure was trying to make the ODE easy to solve. But I'm really hopeful that if we can do this properly, we'll eventually be able to train networks that learn how to be fast or require fewer layers. Right? So right now, there's a major area of research in deep learning that's called distillation, where we say, oh, I've trained my big, expensive model, but I don't want to put that on a phone. So I'm going to train another neural network that's smaller that's almost as good and I can put on the phone. The hope here is that this can all be done automatically at training time, where the model is trying to be accurate and fast. And so, I'm hoping maybe it'll go through a regime where it's, first training an expensive, good model, then learning to distill it down to something easier to compute. So the sort of general intuition here is that if we're solving a system with a fourth order solver, The thing that lets it take long step sizes is if the fourth order derivatives of the state are small. So we can actually compute those and just regularize them. That requires computing the gradient of the integral of the fourth derivative of the dynamics, but we can do that now. We have good automatic differentiation. Okay, and then obviously also, we're just using off-the-shelf solvers and sort of off-the-shelf architectures. We just copied what people were already doing in Resnets. But I'm sure that there is some sort of synergy that can be exploited between choosing what architecture you're using in the ODE net and choosing what ODE solver you're using to solve it. There's also, of course, a lot of related work on learning to solve more generally, like for any ODE solver, like tuning the solver as you go, or adapting the tolerances automatically to say which part of the system do I need to solve precisely and which ones don't I. So that's all for me. I'd like to thank my students, Ricky Chen, Yulia Rubinova, Jesse Betancourt, and Will Grathwall. Thank you very much.